Welcome to The Explainer. The electricity powering the screen you're watching right now, the fuel in the bus you might take to school, well, it all starts with a story that begins millions of years ago, deep underground. Today, we're going to trace that incredible journey of energy.
Okay, so we've all seen a sparkling city skyline just like this one. It's beautiful, right? But the slide asks a really good question. Have you ever stopped to think where all that light actually comes from? The answer isn't just a power plant down the road. It's a story that kicks off millions and millions of years ago.
Over 95%. Just let that sink in for a second. That's not just some random statistic. It means that nearly every single light, every computer, pretty much all the power in a city like this comes from natural gas. It's a staggering number, and it really shows you just how central these fuels are to our modern world.
So the name itself, fossil fuel, gives us a huge clue about where this is all going. To really get it, we need to stop thinking like engineers for a moment and start thinking a bit more like paleontologists, because our story begins way back when dinosaurs were still walking the earth. This definition right here gives us the two most important things you need to know. First, these fuels are literally made from the fossilized remains of ancient life. And second, and this is absolutely critical, they're non-renewable. That means there's a limited supply. Nature spent millions of years making this stuff. We can't just cook up a new batch tomorrow.
And for all you chemistry students out there, this is where it gets really interesting. Chemically, what are these fuels? They're basically hydrocarbons. The name tells you everything you need to know. They're compounds made of just hydrogen and carbon atoms. But crude oil isn't one single pure thing. It's this messy, complicated soup of many, many different kinds of hydrocarbons, all with different sizes and shapes.
This illustration is perfect. It basically captures nature's three-step recipe for making oil. First, you have ancient sea life, tiny little organisms that die and sink to the ocean floor. Second, they get buried under huge, heavy layers of sand and rock. And third, the secret ingredient. Millions of years of intense heat and pressure from the earth, which basically cooks all that organic stuff into what we know as crude oil and natural gas. Okay, let's do a quick recap. What exactly is crude oil? Well, if we pull together everything we just learned, we know it's a non-renewable fossil fuel. It's a really complex mix of all kinds of different hydrocarbons, and it was all formed from ancient life that got cooked under incredible pressure for millions of years. So now we have this thick, black, sticky goo that we've pumped out of the ground. Obviously, you can't put this stuff directly into a car. So the next big question is, how in the world do we turn this raw material into all the useful fuels we rely on every single day?
So, we've got this jumbled up mass of different hydrocarbon molecules. How do you sort them all out? It's a fantastic chemistry puzzle. But the secret, the key to solving it, lies in a physical property you're probably pretty familiar with from your school lab, the boiling point.
Yeah, this little lab setup should definitely look familiar. The principle is super simple. Different liquids boil at different temperatures. If you heat up a mixture, the liquid with the lowest boiling point turns into a gas first. You can then catch that gas, cool it down, and bingo, you've separated it out. Now what we're about to see is what happens when you take this simple idea and you scale it up, like way up.
And that massive scaled-up process is called fractional distillation. Here's the play-by-play. Step 1. You take crude oil and you superheat it in a furnace to about 400 degrees Celsius, hot. Step 2. This turns most of the hydrocarbon mix into a hot vapor. Step 3. This gas is then pumped into the bottom of a giant tower, a fractionating column. As it rises, it starts to cool down. And Step 4. This is the clever part. Different hydrocarbons cool and condense back into a liquid at different temperatures, which means at different heights in the tower, where they're collected on trays. It's kind of like a skyscraper for sorting chemicals.
Now, what I think is so cool about this slide is the contrast. On the left, you have that simple diagram we just talked about. On the right, bam. That's the reality. These are the giant fractionating columns on Jurong Island in Singapore. It just shows you the incredible engineering it takes to apply that one simple scientific principle on an industrial scale. So after all that heating, rising, cooling, and separating, what do we actually get? What are these different fractions that we collect from all the different levels of the tower?
The stuff that comes out of the distillation column is pretty amazing.
From the different levels, we get everything from cooking gas and petrol for our cars to kerosene for jet engines and diesel for lorries and buses. And even that thick, sticky gunk left at the very bottom, bitumen, is what we use to pave the very roads we drive on. It's a whole range of essential products, all from one single process.
This quote right here, this is the golden rule. It's the single most important idea to understand how this all works. It's all about boiling points. The hydrocarbons that are easy to turn into a gas, the ones with low boiling points, they're going to travel all the way up to the cooler top levels of the tower before they finally turn back into a liquid.
And this creates a really clear, predictable pattern. At the very top, we collect the fractions with low boiling points. These are made of small molecules, and they catch fire really easily. Think petrol. Then, way down at the bottom, we get the leftovers with super high boiling points. These are made of huge, long-chain hydrocarbon molecules. They're thick and gooey, and that's our bitumen for roads. Small molecules at the top, big molecules at the bottom. Simple as that.
But here's the challenge. This incredibly useful resource is finite. It's running out, and we have all these competing demands for it. So we have to make a choice.
This chart reveals a pretty shocking reality about the choice we're currently making. Just look at those numbers. A staggering 90% of the crude oil we refine is simply burned for energy. That leaves just a tiny 10% to be used as what's called a chemical feedstock, the actual building blocks for making other materials.
And that 10% is incredibly important. It's what we use to make plastics, medicines, fertilizers, you name it. Countless products we need every day. So the crucial point is this: we face a big choice. Every single drop we burn for energy is a drop we can't use as a precious raw material for manufacturing. So, do we burn it or do we build with it? That's the big question.
Now, this challenge has led scientists and engineers to look for alternatives, especially for the burning part of that equation. And this is where biofuels start to enter the story.
So what's the alternative idea? Well, instead of drilling for ancient buried energy, we can look to plants that we can grow right now. This diagram shows the process for making bioethanol from sugarcane. You basically just crush the cane, use yeast to ferment the sugars inside into alcohol, and then you distill that to get your fuel.
So let's compare them head to head. Fossil fuels come from ancient, dead stuff and are non-renewable. Biofuels come from recently living plants and are renewable. The key difference here is all about time. One takes millions of years to form. The other, you can grow a new batch in a single year. So why do people say this is more sustainable? Well, the key is the carbon cycle. When you burn bioethanol, yes, it releases CO2, just like fossil fuels. But, and this is the really crucial part, the sugarcane plant already sucked that CO2 out of the atmosphere while it was growing. So in theory, it creates a kind of closed loop, which is the core idea behind why it's considered more sustainable.
And so, our journey through the world of fuel leaves us right here at a crossroads. We've seen how this ancient buried energy was transformed to build the modern world all around us. But now, knowing that this resource is finite, and knowing we have this incredible choice between burning it for fuel or building with it for the future, the question on the screen isn't really for scientists or politicians, it's for all of us. What path are we going to choose?